Welcome to the office. We want to talk about the division algorithm, and we're going to use the division algorithm here in abstract algebra or modern algebra to help us demonstrate something about cyclic groups. So this idea of the division algorithm itself is not, right, this is not abstract algebra content. Rather, it's content that really should be background maybe from either a proofs course or discrete math, that sort of thing, that we're going to bring into this course. But just in case you haven't seen it before, let's go ahead and take a look at it. All right. The division algorithm says that if m is a positive integer and n is any integer, then there exist unique integers q and r such that n is equal to m times q plus r. Now, if you're thinking of division in the integers, which is where we're working here, if you think of the simple idea like, oh, I don't know, 20 divided by 6. Okay, 20 divided by 6 is going to be, you may have thought of this as 3 with a remainder of 2 because, right, 6 times 3 is 18, so you have a remainder of 2. So this looks kind of weird, but it's along the right ideas. What we want to recognize is that maybe a better way to write this would be 20 divided by 6 is equal to 3 plus 2 divided by 6. And if we were to take that and multiply both sides by 6, we would get that 20 is equal to 3 times 6 here. Well, actually, let's go ahead and say that it's, oh yeah, no, that's what I want. 3 times 6 times 6 plus 2. Once I multiply both sides by 6. Oh, so actually, yeah, I did want to write this in the other order. It doesn't matter, right? Multiplication is commutative. So whether you change this or not, that's fine. 6 times, not 6, 6 times 3. There we go. So 20 is 6 times 3, 18 plus 2. Fantastic, not a big deal. And this idea that we can talk about division and have remainders is exactly what we want here, which is exactly the form that we're looking at for the division algorithm. Wonderful. So if we have integers m and n, positive anything, there are integers q and r, right, quotient and remainder, such that n, 20 for example, is equal to m, which is what we divided by, times the quotient, 3, plus the remainder, 2. Okay, so we see a basic example here where we look at it from the perspective of, hey, we're performing some division, hence division algorithm, whereas in our following examples, we want to recognize this particular form to begin with when 17 is divided by 6. Okay, so if we wanted to look at that, this would essentially be taking a value for m and a value for n. I want to make sure that I say that correctly. Oh, I said that backwards. N and M. N is the thing that we are dividing. M is what we are dividing by. In other textbooks, they use D for the thing that we're dividing by, divisor. All right. So if I wanted to express it in this way, I'm trying to say that 17 is equal to, oh, well, I'm not very original here, dividing by 6 again. So I want to write this as n is equal to m times something. N 6 times, we'll go 2 in this case. 6 times 2 is 12, and then plus 5. So this value of r, we want to be between 0 and m. So we're always adding something positive. But we can also, right, well, that's worth pointing out because we just showed that 6 times 3 is 18, and I wouldn't want to say that 17 is 18 minus 1. I want this to be additional always. Okay, that makes it unique. If I want to find the quotient, oh, that was supposed to be a q, and remainder, when negative 17 is divided by 6, then I'm going to say negative 17 is equal to 6 times. Now this is going to be a negative number, and I do want it to be negative 3. 6 times a negative 3 is going to give us a negative 18. So that way I can add a positive number. I can add 1 to take us from negative 18 up to negative 17. So this remainder here is always a positive number. All right. We'll encounter primarily this situation where both of them are positive, but it's worth pointing out that we can have a number that we're dividing, which is negative. Okay? Excellent. That's all I wanted to share about the division algorithm. This sort of idea will become useful for us as we look to prove the next theorem. So join me back in the office in a moment for exactly that, our next theorem.